Imagine a wall standing in the middle of the sea, so long that the horizon itself seems split in two. On one side, yellow sea waves still strike the rock slope. On the other, water has been held back by humans. The seawall stretches 33.9 kilometers, linking the coastal areas of Gunsan and Buan with a completely artificial boundary. Behind it lies a plan for 291 square kilometers of reclaimed land and 118 square kilometers of managed water. But scale is not the hardest part. The tides keep reversing and forcing water through every remaining opening. By ordinary logic, a seawall tens of kilometers long on weak coastal ground should be highly vulnerable to erosion. And the closer construction gets to closure, the more the remaining gaps concentrate the flow into faster, stronger currents. If the drainage system stopped, river water and rainfall inside would continue accumulating behind the barrier. If a slope became unstable, waves would not need to destroy the whole seawall. They would only need one weak point. If the final gap were handled badly, tidal flow could remove material faster than construction could replace it. Yet that artificial boundary still stands, carrying a roadway and enormous sluice structures across the coast. Water was not defeated. It is guided, stored, released, and monitored through a system that must keep operating. From above, the structure resembles a gigantic lock, closing the sea while still leaving controlled passages for water. This is the Saemangeum Seawall, a major barrier on South Korea's west coast facing directly into the Yellow Sea. The real question is not who dumped the most rock, but how to close the sea while the water keeps moving. Before the seawall existed, Saemangeum was a vast estuary where fresh water met tides across broad coastal mudflats. The Mangyong and Dongjin river systems carried inland water into an open estuary facing the Yellow Sea. Each tidal cycle pushed seawater inward and pulled it back out, continuously reshaping the flow channels across the flats. Here, the shoreline was never a fixed line. It shifted with water level, sediment, and the changing seasons. That is why coastal reclamation is completely different from simply expanding dry land on the mainland. The seabed can be soft, waterlogged, and deformable under heavy loads, while waves continue acting above it. Studies of Saemangeum recorded a large tidal regime, with spring tidal ranges that could approach 7 meters. That turned every opening between unfinished dike sections into a temporary estuary carrying powerful two-way flow. To create new land, engineers first had to do the opposite of nature, turn open water into bounded water. So the original idea did not begin with a road on top, but with controlling the boundary between water masses. Construction began in 1991, when the project's goals were still strongly tied to creating agricultural land. Instead of filling the entire estuary at once, the strategy was to build an outer barrier first. The outer line was divided into sections, using land points and islands to shorten the stretches built entirely across water. That choice mattered because every natural anchor reduced the distance that had to be constructed in open water. But the islands only divided the problem. They could not remove waves, tides, or the weak seabed beneath. From the beginning, the project was a struggle between the geometry of the design and the living terrain of the estuary. A straight line on a map had to become a three-dimensional structure, heavy, wide, and stable enough to hold water. And before the first major load was placed, engineers had to understand what the seabed was hiding beneath the mud. Bathymetric surveys revealed where the seabed was deep, where tidal channels ran, and where currents concentrated most strongly. Geotechnical surveys answered a different question. How would the foundation behave as the growing seawall became heavier? On soft ground, dumping faster does not always mean building faster. Loading too quickly can deform the foundation. So the seawall had to rise in stages, giving the ground and materials time to adjust to each new load. Dumped rock formed the rough skeleton, adding mass while still allowing water to pass through before the structure became tighter. Large rocks also resist currents better than fine material, which moving water can easily pull away from position. At first, the seawall did not need to become perfectly watertight. It needed to become a stable foundation. Construction advanced gradually from shorelines and anchor points, while transport equipment continuously carried material toward the sea. Each delivery added only a small amount, but repeated placement errors could accumulate into a major geometric deviation. That is why elevation, width, and slope shape had to be checked constantly while the water level kept changing. Once the core took shape, earth and suitable graded materials made the seawall thicker and less permeable. The seaward slope had to resist waves and erosion, so it was protected with heavy material and a broad, gentle profile. The inner slope faced different conditions, but still had to remain stable as water levels and sluice flows changed. The seawall is therefore not a vertical wall. It is more like an extremely long artificial hill lying across the sea. Its own mass provides stability, while the outer protection receives the repeated blows of waves. This was the structure's first adaptation, resisting water not through thinness, but through mass and geometry. But as the dike sections extended, water was forced to use fewer and fewer paths between inside and outside, and the success of the early stages began creating a more dangerous hydraulic problem for the final stage. By then, the site was no longer a collection of isolated rock sections. It had become a system coordinated around the tides. Construction schedules had to match weather windows, water levels, and the ability to deliver material at the right moment. Hydrological measurements tracked current speed, flow direction, and water level to identify where loads were becoming greatest. Crews on the seawall depended on that information because a delayed decision could allow the current to change state. Materials also had different roles. Large blocks resisted movement, smaller stone filled voids, and earth improved water tightness. Where waves struck directly, the slope had to dissipate energy instead of reflecting the full force of the water. A gentle armored slope lets waves climb, break, and lose energy before reaching the highest part of the seawall. Crest elevation had to account for tides, waves, and overtopping risk, not merely the average level of the sea. But keeping seawater out was not enough, because the two rivers inside continued delivering fresh water into the enclosed area. So the system required enormous sluices, functioning like regulating valves between the inner lake and the outer sea. The sluices cannot simply stay open. Timing determines which way water moves and how strongly it flows. When outer water is suitably lower, the difference in level can help drain interior water outward by gravity. Under other operating conditions, opening the gates can also admit seawater, altering salinity and mixing inside. So a wall that looks motionless actually contains moving components that must operate precisely for the system to function. Saemangeum includes the Cincy and Garrioch sluice complexes, major points of controlled exchange between the two water bodies. They transform the seawall from a simple obstacle into hydraulic infrastructure capable of directing and regulating flow. At this scale, a giant sea lock cannot have only a door. It needs hinges, valves, and people to operate it. That is when the project shifted from asking whether it could be built to asking whether it could be operated. Every completed section reduced direct tidal exchange, meaning the flow patterns inside changed with each construction stage. Monitoring therefore had to continue, because conditions after each stage were no longer the same as before. The seawall, sluices, inner lake, and drainage routes therefore had to be treated as one connected hydraulic body. And the hardest part of that body lay where water was squeezed through the final remaining openings. To understand the danger of the final gap, imagine the same amount of water forced through an ever narrower passage. As the passage narrows, flow usually accelerates, increasing erosion around the seabed and along both edges of the opening. Freshly dumped rocks can roll, slide, or be swept away before the next layer has time to lock them in place. Scour at the toe is even more dangerous because it removes support directly beneath the advancing seawall. So the goal is not merely to fill the opening, but to reduce the current's energy before complete closure. One method is to gradually raise a rock sill across the full width, spreading the flow over a broader area. As the sill rises, deep water decreases, and engineers gain more control over where the next material can be placed. This is the vertical closure component. The seabed is raised before the visible embankment connects completely. Construction can then advance horizontally from the ends, narrowing the remaining opening in a carefully planned sequence. Combining both directions avoids concentrating the entire struggle too early into one deep, violent channel. But every meter of narrowing changes speed, eddies, and water level differences, so the design must respond to real conditions. Near the bed, local vortices can form around rocks, removing finer material and creating pockets of scour. At the surface, waves act on a different rhythm, forcing the same structure to endure two continuous types of loading. Material size, therefore, cannot be chosen by instinct. Each block must be heavy enough for the forces at its location. Large blocks provide mechanical anchoring, while smaller material fills the voids and reduces internal movement. As those voids shrink, seepage through the seawall weakens, and the structure begins transitioning into a water-retaining barrier. Earthfill does more than bulk up the embankment. It helps form a lower permeability zone deep inside the structure. But a tighter seawall also creates clearer water level differences, making seepage pressure a new problem to manage. Water always searches for paths through pores, beneath foundations, or around structures, so internal drainage must be considered. Rock and earth seawalls are therefore designed with several functional zones rather than as one random pile of mixed material. Each zone has a job: carrying load, filtering particles, reducing seepage, protecting slopes, or supporting operations above. On the seaward side, protection must absorb waves without allowing finer material behind it to be sucked outward. If fine particles are gradually removed, the slope can hollow out internally before obvious damage appears outside. Erosion control is therefore a battle against small, repeated losses, not only against one exceptional wave. On completed sections, the crest provides space for roads and equipment, while the hydraulic structure remains hidden below. What drivers see is only the upper surface of a very broad cross-section containing several different material zones. At the sluices, the problem changes completely. The structure must let huge volumes of water pass through safely. Flow is confined within rigid bays where the structure directs water away from the softer earth and rock embankment. When gates open, velocity can rise sharply near the outlet, so the bed and banks nearby require strong scour protection. When gates close, the gates themselves must resist the pressure difference between the two bodies of water. Operation is therefore tied to the tide, because opening at the wrong moment can send water opposite to the intended direction. The Cincy and Garrioch gates let managers shift from passively accepting tides to choosing when exchange occurs. But control is never absolute. Heavy rain and river inflow can change the amount of interior water very quickly. The inner lake therefore needs storage capacity, while sluices must be ready to release water when conditions allow. When water levels are lowered, shallow areas remain exposed longer, and the process of creating land can continue. The key point is that finishing the seawall does not create new land. It only creates the conditions for reclamation to begin. As the barrier neared completion, the estuarine ecosystem also began operating under a fundamentally different set of rules. Tidal range inside fell sharply, changing the old rhythm of areas that once flooded and emerged with every cycle. For bottom-dwelling organisms, changes in inundation time can matter as much as changes in temperature or salinity. Studies at Saemangeum recorded shifts in benthic communities as tidal energy inside the system declined. Tidal flats that once served as feeding grounds for migratory birds were also reduced or changed ecologically. Meanwhile, freshwater rivers continued carrying nutrients and sediment into a basin that exchanged less freely with the sea. When water mixes less, stratification can become stronger, especially during seasons with large freshwater inflows. Surface and deeper layers can then differ in salinity, temperature, and dissolved oxygen. That is the hidden price of controlling water. The more tightly the boundary is controlled, the more the interior must be managed. Sluices therefore do more than prevent flooding. They directly influence mixing and environmental conditions inside the lake. Each opening can send seawater inward or interior water outward, depending on tide and water level differences. Too little exchange can leave water stagnant, while too much can conflict with desired salinity conditions inside. There is no single gate setting that solves everything, because the system must balance water management and environmental needs. The outer coast is not static either. Changing tidal pathways can alter erosion and deposition patterns beyond the seawall. Areas that once received dispersed flow may receive more concentrated current, while other areas may accumulate additional sediment. So the effects of a seawall do not stop at its base. They travel with the currents the structure redirects. Saemangeum became the focus of prolonged environmental debate precisely because the estuarine transformation was so large. The debate does not deny the engineering achievement. It asks how far engineering responsibility extends after completion. A structure can be geotechnically stable while still creating ecological consequences that require monitoring for many years. That is the difference between completing a structure and completing responsibility for managing the new water environment. The sea lock now carries a deeper meaning. It restrains the tide, but it also restrains many natural processes. And when those processes change, humans must replace part of them with operation, monitoring, and adjustment. During final closure, every earlier engineering problem converged on the remaining openings between the sea and the interior. One northern opening had already been closed, while the final two gaps still carried much of the tidal exchange. On April 21, 2006, the final two gaps, totaling about 2.7 kilometers, were closed at the same time. This was not a moment of dumping one line of rock and finishing. It was a campaign to reshape the flow step by step. First, the underwater sill was gradually raised across the full width to reduce the effective depth of the current. Every new layer changed the flow, so the next placement had to consider both current velocity and the coming tide. As the artificial bed rose, the operation shifted from vertical closure toward horizontal narrowing. Dump trucks moved onto the newly formed embankment, carrying material close to the edge where water still swept past. There, material was not dropped into still water. It entered a current still trying to reopen a path to the sea. Large stones created anchoring mass, but the spaces between them still let water through and could destabilize the structure. To improve stability, the final closure also used stone-filled mesh bags together with dumped rock. Those flexible units could conform more closely to irregular seabed surfaces and help stabilize material in powerful currents. The shorter the opening became, the more quickly each new placement changed the hydraulic conditions around it. This is the paradox of the final stage. The closer construction gets to success, the less predictable the remaining gap becomes. The crews were racing not against the clock itself, but against the changing rhythm of the water. When the final material fronts met, direct tidal flow through the gap stopped, but water pressure did not disappear. It shifted toward the sluices, seepage paths, lake level, and every supporting system that now became essential. So closure was not the final victory. It was the moment the entire project changed operating modes. Before closure, the sea exchanged freely through gaps. Afterward, most exchange had to pass through controlled infrastructure. The giant sea lock had finally closed, and from then on, people had to keep the key in hand every day. At this climax, Saemangeum's true nature became clear. The seawall did not remove water. It moved water into a management system. Every later decision had to answer new questions: what water level to maintain, when to discharge, and how to develop the land. After closure, work shifted from building the outer boundary to managing the enormous water body enclosed behind it. The sluices became the center of operations, draining river water and regulating exchange with the Yellow Sea. The Cincy complex has 10 large gates, while Garioch has 8, giving the system major flow control capacity. Each main gate is about 30 meters wide and about 15 meters high, showing the scale of water the system must handle. But size is only the hardware. Deciding when and how long to open the gates is the software of the project. Water level, tide, rainfall, and water quality data therefore became essential inputs for daily operation. When water must be lowered, the gates can use the level difference with the sea to drain the interior outward. When environmental goals require exchange, operations can also allow seawater inward under suitable conditions. The inner lake is therefore not completely isolated, even though its exchange rhythm is now very different from before. At the same time, inner embankments and zoning infrastructure divide the reclamation area into sections that can be developed gradually. New land does not appear from one massive fill operation. It forms through lowering water, drainage, and staged filling. As shallow areas become drier, they can be strengthened, raised, and prepared for new uses. Each reclaimed zone needs its own drainage system because rainfall on new land must still find a route to the sea. Land reclamation does not end at the outer seawall. It creates a secondary water management network inside. Water quality monitoring also becomes permanent because land development further changes runoff patterns and pollutant loads. After the climax, the project behaves more like an operating system than a wall that can simply be finished and abandoned. Every rainy season, every tidal cycle, and every new development stage creates a different set of operating conditions. Saemangeum's answer after 2006 was no longer to build faster, but to manage more precisely. The most common misunderstanding is that Saemangeum is simply a long road over the sea, with the seawall serving only as support. In reality, the road sits on top of a massive structure whose main job is to separate and regulate two bodies of water. A second misunderstanding is that closing the seawall instantly turns the interior into dry land ready for construction. In reality, much of the area remains water and must be drained, divided, and treated over time. A third misunderstanding is that the sluices are used only during flood risk, like simple emergency valves. In practice, gate operation affects water level, salinity, mixing, and ecological conditions throughout the interior. And the final misunderstanding is that the tighter the seawall, the better, as though every drop of seawater entering means failure. In a transformed estuary, controlled water exchange can sometimes be necessary to support water quality. That reverses the original intuition. Success is not absolute isolation from the sea, but the right degree of control. Saemangeum is therefore not a story of humans defeating water, but of humans accepting greater responsibility for it. Seen this way, the seawall is not a full stop. It is a colon opening into the long phase of management. Today, the land inside is planned for far more varied functions than the project's original agricultural focus. Official planning identifies 291 square kilometers of land and 118 square kilometers of water across Saemangeum. That changes the engineering question from keeping the sea out to organizing an entirely new territory inside the barrier. Roads, industrial districts, urban areas, and new infrastructure all depend on reclaimed ground being stabilized and drained. But as development expands, rainfall, wastewater, and water quality demands make the operating problem more complex. So Saemangeum's future depends not only on seawall height, but on data and water management decisions. Long-term monitoring helps detect changing erosion, declining water quality, and ecological responses across the system. Under climate change, sea level rise and extreme rainfall can place additional pressure on the assumptions behind older designs. The best solution, therefore, may not be to make every wall higher and every boundary tighter. It may be to coordinate seawalls, sluices, water storage space, forecasting, and adaptive land use planning. This is the modern shift in thinking. An artificial shoreline remains resilient only when the whole interior is operated as a living system. Saemangeum moved the boundary between land and sea, but that new boundary must still negotiate with water every day. A megaproject of land reclamation therefore does not truly end when the outer seawall is finally closed. From high above, the seawall still looks like a thin line drawn between the open sea and a reshaped water landscape. But beneath that thin line lie rock, earth, sluices, seepage paths, and decades of engineering decisions layered together. The sea lock now does more than close a door. It forces people to learn how to live with the vast room behind it. Saemangeum reminds us that building a wall in the sea does not defeat water. It only changes where the dialogue continues.